Good afternoon, everybody. It is a great pleasure to welcome Professor Harald Raupenstrauch from the University of Leoben. Harald is here at the Technical University of Crete as part of the cooperation among the partners in the EURECA-PRO University. And Harald is I mentioned he's a professor at Leoben University. He is trained as a chemical engineer with a PhD from Crete University of Technology. He taught at Crete University of Technology, and then he joined the University of Leoben, and he's also been a visiting professor in many universities, Rutgers University in the States, Delft University of Technology in the Netherlands, the Queen's University of Belfast, the University of Zambia, and Lucerne University in Switzerland. Today's talk is the thermal processing technologies at Montanuniversität Leoben, and we're very happy to have you here with us, Harald, and we're looking forward to your presentation.
Thank you so much for your very kind words and for your great hospitality. I enjoy to stay here a lot. That's most difficult to get everything running. Yeah, thank you so much. So, thank you again for your introduction. So that means I can save this first slide that shortens the presentation. Maybe a few words on the aim. Why am I here? Of course, it's due to the EURECA-PRO University and very good cooperation between our universities. But my thought was just to maybe deepen the relationship by more common scientific projects. And that was the idea to visit you and talk a little bit about some projects where we are working on. So, of course, most of you know the Montanuniversität Leoben, especially the colleagues from Leoben, of course. I will talk a little bit about my chair, and then I will talk about selected topics on high temperature processing technology. I will keep it short because the whole presentation would be nearly 130 slides, which would be too much for today. So I will talk about the problem, why we are working on that, how we deal with it, and what are the solutions. But all the details you can find in the complete presentation, which will be uploaded, and you can have it with all the analytics and everything. And finally, I will talk a few words about our new master program in Leoben, because maybe this could be another opportunity for a cooperation. So, some of you visited Leoben already, so our campus is distributed in the city center of Leoben, which is quite nice because everything is very close. There's a good combination between university, the restaurants, the people living there. Our university was known as University of Mining, but of course during the last couple of years or even decades, we transport to a university dealing with responsible consumption and production. We do science and teach advanced resources, sustainable processes, smart materials. And that was also one idea of this European university. At the moment, we have about 13 bachelor's programs, 25 master programs, some of them in English, most of them still in German, and which is maybe not that often for a technical university with about 26% female students. We have students from 89 different countries, which is quite a lot. Yes, and then a few words of my chair. My chair is a part of the Department of Environmental and Energy Process Engineering, and this department consists of 4 different chairs. One is my chair of thermal processing technology. Another chair is the chair of waste processing technology and waste management. where a big conference is going on right now in Leoben since Wednesday. Then we have the chair of process technology and industrial environment protection, Professor Lehner, and the chair of energy network technology, Professor Kimberger, who will have a presentation via EURECA-PRO on Monday morning, I learned. So our chair, we have about 45 employees, including employees financed by K1 Med. That means we have about 4 senior scientists and 9 PhD students. My chair consists of 4 working groups. Working group Industrial Energy Engineering, Mathematical Modeling and Simulation, Safety and Disaster Studies, and the one I will talk about in more detail today is a high temperature processing technology, where we are dealing with recovery and recycling processes. This is the group. So I'm just the conductor. So the experts are my colleagues. You can see here on the photographs, you have all the details like phone number and email. So when you read through the complete material you can download, you can contact them also directly with more detailed questions. So what is the main idea of this group? We are working on defossilization and climate neutrality. Why not decarbonization? I don't like this word because we will always need carbon. The main idea is to get the carbon not from fossil sources, but from renewable sources, and therefore defossilization is the better word. You will see the way we treat these problems, we are focusing on a sustainable circular economy. So that means we are looking for residues from different processes and try to upgrade them, to combine them with other residues. In addition to that, we are aware of the fact that we are specialists in certain areas, but we also have to, we always have to look at the complete process. That means we need other experts from science or from industry to deal with the problems more adequate. So we are very open for collaboration, and the outcome of this science, the results, is always the basis for our education for students and PhD students. So let's start with an example on carbon-thermal treatment and cooling of metallurgical residues. Start with the cement industry. Cement industry is known as one of the big carbon dioxide distributors. So worldwide, the emission of carbon dioxide is about 2.42 gigatons. It comes on the one hand side from the energy, but on the other hand side due to the chemical reaction of the calcination. So one idea is to substitute the clinker of the cement in the cement production by blast furnace slag, for example, or fly ash from coal. So both sources won't be available in this amount in the future, because the blast furnaces in Austria plan to shut down completely. Worldwide, they will be reduced. Even coal combustion is not available in Austria anymore. So these secondary sources are not available for the cement industry. So let's have so that obviously the iron and steel industry is very connected to the cement industry, because their slags, part of the slags go directly to the cement industry. So if we have a look at the numbers, at the moment, a big share of the steel production is based on the blast furnace, and this will be reduced in the next couple of years, decades, dramatically due to the shift from the blast furnace to electric steel making or other green technologies. And if we have a look at the slag as byproduct, we see for the blast furnace EOF route between 390 and 560 kilograms per ton crude steel, or EAF route 185 to 265 kilograms per ton crude steel. And this won't be available in future. So what is the idea? Our research objects are first, how to recover valuable metals like iron, manganese, chromium from secondary raw materials of the scrap-based steel production, which will be more important in future. Then develop alternative supplementary cementitious materials for the substitution of the granulated blast furnace slag, because they won't be available in future, at least in Austria and Central Europe. Of course, we want to avoid landfilling of metallurgical residues. We'll see that later. We want to investigate possible energy recoveries. If we think about the slag and the high content of energy, if you just cool it without energy recovery, you'll lose a big share of energy. And in future, we will have new slag types. So it's necessary to characterize them and maybe even create new slags, which are easier to use in other processes. So what is the idea of my research group? The head of the research group is my senior scientist, Klaus Doschek-Held. So we have metallurgical residues, and these residues have to be corrected. We'll see later on why. So we need some correction materials, and the idea is to use correction materials which are residues from other processes. And then the chemothermal reduction takes place, therefore we need a reducing agent. It should be maybe called a green reducing agent, maybe not fossil coal. And we need a lot of energy. So this energy should be green as well. Then the takes place, should go directly to the slag fraction. If it meets the requirements, should go directly to the cement industry. That's the principal idea, and this idea you will see frequently today when I talk about other topics. So the reference material for this research is the granulated blast furnace slags, but we treat a lot of slags from integrated steel mills, electric steel making slags, and as a correction material we use basic oxygen furnace slag, Siemens Martin slag, gas waste, but you can think of any other slag as well. So here's the principle. In this triangle diagram, you see the composition of the materials we are talking of. So the reference material is this little star you can see here in this red marked area, and the red marked area is the desired area where our material, the composition of the material should lie. So all the other slags and correction materials are lying somewhere in the triangle. And the idea is to combine it in that way that the mixtures of these materials end up in the red marked area, because then we have the right properties for the process, for cement industry, for example, and that's the main idea. So the first step, what we are doing with the mixtures, we make lab scale experiments in this resistance elevator furnace for small quantities. We melt it to the chemothermal treatment. The next step is with larger amounts of samples in this inductively heated crucible furnace. We will talk about inductively heated furnaces later in more detail. Here we have larger quantities. We treat them with the reduction experiments, and after that we cool them. So how do we cool the slag? Traditionally, we use wet quenching. That's very simple. It's state of the art. You just quench it with water. The process is quite stable. What is the disadvantage? You produce wastewater on the one hand side. You have formation of hydrogen sulfide and water vapor, and this water vapor cannot use for energy recovery. Looks like that. Another way is spinning disk atomization. That means you produce hot air, and this can be used for heat recovery, and you don't need any fresh water. What is the disadvantage? It's more complicated. It needs higher efforts in process engineering, and it's more sensitive to material properties. The word slag is such a simple word for such a complex material, because as soon as you change the properties a little bit, or the temperature, the viscosity and everything changes dramatically. And this is important for this process. So why do we need granulation then? Well, we need an amorphous structure to use it as a reactive binder component for the cement industry. And this gaseous solidification can only be achieved by rapid cooling. If you cool too slow, you produce wool instead of spheres, granulates. And other advantage is you need less efforts for crushing it. And it's easier to separate the metallic fractions from it. So why is this cooling? It's not only for the slags we are talking about. The cooling of slag is a principal worldwide problem. About 400 million tons of blast furnace slags per year are cooled down with water. That means about 1.5 gigajoule a ton energy is unused. So if you can granulate it, cool it down really fast, not with water, but with air. This is one possible principle. You heat up the air, and this hot air, in this case, the air would have a temperature of about 650 degrees centigrade, can be used for producing steam and electricity, or what else. So we treat this material and then we characterize the output, the mineral fraction, interesting, the chemical composition, the gas content, and for the cement industry, for completed, this R3 testing procedure is important. And for the metal fraction, the chemical composition and the reduction rate. The details you can find in the uploaded complete presentation. What are the conclusions? By treating the material in that way, we get the desired chemical composition. We can achieve the rapid cooling, in this case, with a gas content of about 66%. Talking about the metal fraction, we could separate the mineral fraction from the metal fraction. We could efficiently recover iron and manganese. And the iron content in the recovered metal alloy makes it suitable for use as SRM, as a secondary raw material in the metallurgical industry. So what is the outlook? And the outlook is always interesting because maybe we get some input from other scientific partners for this work. Improve the metal recovery, especially the manganese recovery. Investigate other treatment processes and cooling methods. So there are various methods to cool the hot granulates, which are maybe even simpler than the one we used. Implement machine learning, one of the next steps. And what is really crucial to determine the viscosity and the melting rate of the slag. It would be nice to measure the viscosity of in situ. Now we have to measure somehow the temperature, and even that is not too easy, to measure the temperature of a slag to the effects you know. So, and then calculate the viscosity. So it would be nice. That's a problem for the gas industry as well. So if you could measure the viscosity of the gas phase when it fills the forms for forming the bottles, and if you could measure the viscosity inline, it would be a big advantage. Yes, and we are working on the holistic prediction tool. So if you know all the materials, the properties of the materials, and you can calculate the resulting fractions and their properties after the treatment, it would be really helpful. So another potential way for secondary raw materials, mineral wool waste is mineral wool waste recycling. So mineral wools, what are mineral wools? It can be stone wool from basalt, for example, or glass wool from quartz and soda limestone. And this is used widely in construction for isolation. So you have the raw material, you produce the mineral wool, and even during the production, you have you produce a little bit of waste. Then you use it in construction to isolate houses, for example. Then you have construction waste, about 5%, which could be used again. And the next one is after the end of life, you when you, for example, if the houses are at end of life and you have to destroy them, then you have a big share of this demolition waste, which is about 95%. And this construction waste is the recycling is limited by chemical composition, and on the other hand side, the demolition waste makes some problems. On the one hand side, landfilling is always a problem because you could use it. And on the other hand side, it's not very stable, so you get stability problems in the landfill. So what is the idea? Same idea as I demonstrated earlier. We have this mineral wool waste. We're looking for correction substances, make briquettes out of that, and then we keep treat it thermally, we cool it, and then we have a stacked fraction. So quite similar this procedure as I explained earlier. So we have here our triangle diagram again. The desired area is marked red already. This target area comes from the stakeholders or even from norms. And we see all this material we're talking about are far away from this desired area. But if we combine them properly, we come into this target area, and we can handle it by carbo-thermal treatment, and then we can cool it down, granulate it. This is just a lab scale setup, but it still looks quite nice. So that's nice about high temperatures. It's always glowing and something is going on. So what are the results? So similar, the production of this processed mineral wool, the result is light granulated blast furnace, which is makes us quite hopefully. And the result, the properties are can be used of this. This material can be used as a secondary material for cement industry to substitute clinker. Of course, there are some other topics we are working on to identify the influencing parameters for the treatment of this material and to examine other correction materials. For example, this dust from cement kilns. So, but there's a wide variety of correction materials. And the next step would be a pilot scale, because at the moment we're just working on lab scale. One big topic is phosphorus. So phosphorus is one material which you cannot find not much in Europe, so most of the phosphorus comes from Russia, from Morocco. Why is phosphorus that important? Did you think about how much phosphorus you have in your body? About 1% of your weight. It's important to transform the food to energy and so on. So it's really important, and you cannot substitute it in the body. That means we have to get some phosphorus from the food, but since no process can be run at 100%, you leave part of the phosphorus, and this ends up in the sewage sludge. So the sewage sludge contains a big amount of phosphorus, animal waste, for example, as well. So now there are different utilization options for this phosphorus. You could spread it direct on the field, which is done very frequently. You can compose it, but the problem is you have also the undesired components in the sewage sludge, like hormones, drug residues, heavy metals. So it's not allowed in Europe in many countries anymore, or it won't be allowed in future in many countries. So you could thermal utilize it in a mono incineration, for example. Co-incineration is state of the art, but in this case, the phosphorus in the ash is diluted, which is not very economical. Or you could pyrolyze it, and then you have carbon and phosphorus. So just to get an idea how much phosphorus is in the sewage sludge ash, it varies. It's completely different. It's a question where this sewage sludge ash comes from. But you see about 20% P2O5 is in this ash, which is quite a lot. But you also see you have an iron oxide content of nearly 17%. This iron oxide comes from the sewage sludge plant. And this can cause problems because the phosphorus tends to react very rapidly with the iron and creates iron phosphate. A couple of years ago, more than 10 years ago, we had a EU project called EURECA-PRO. It was a 3 years project funded by EU. Our university was the project coordinator, and we developed a new process to produce white phosphorus out of the, so not a fertilizer, but white phosphorus out of the sewage sludge ash. What is the main idea? This is the main reaction to produce phosphorus out of the sewage sludge. You have this bounded phosphorus in this calcium P4 times, and you need silicium oxide as for slag formation. You need carbon because this chemical reaction takes place under reducing atmosphere, because in this case you can reduce the phosphorus oxide, produce phosphorus and carbon monoxide. So that sounds quite simple. It's similar done with the rock phosphate by the Wöhler process. This is commonly known, so the same chemical reaction takes place there. But showing this picture, you see the problem. You have the electrodes, so you bring in the energy, create the high temperatures. You have the rock phosphate in this packed bag, you have the silicium oxide, you have the carbon, and produce out of the carbon, due to the high temperatures, the carbon monoxide, and that reduces the P2, the phosphorus oxide. But if you have a look at these electrodes, you can imagine you have a temperature distribution around the electrodes. You have high temperatures and further away low temperatures. That means that the chemical reaction conditions are completely different, and that means that the phosphorus may end up as desired in the gas phase, but it can also react with the iron phase. Then you have it in the metal component, and a part of it remains in the slag phase. So the transfer coefficients are not very ideal, because we want to get all the phosphorus in the gas phase. So that was the idea for this project. So we have we created a reactor which is similar on the one hand side, but completely different on the other hand side. So this reactor contains of graphite particles, and these graphite particles are heated with induction coils. In this case, we have 3 induction coils, and this gives us the possibility to create the desired temperature profile in flow direction and across the flow direction. That means we have a temperature profile in the flow direction, the even smooth temperature profile across the flow direction. That means we can define the reaction conditions very precisely. And then we can decide where the flue gas spike should be to get out the phosphorus from there. So, and that's an example for the temperature profiles you see simulated in this case. So you even see the necessary heat. The big share of heat to put in is to melt the ash, more than, in this case, 50%, but it can be even more. So you can reduce this share if you combine the thermal pre-treatment and feed the hot ash into this reactor type, and you can save this money for this energy. And then you have the proper temperature for the chemical reactions. It's a very simple figure on the left-hand side, because we have a solid phase, we have 2 liquid phases, slag phase, metal phase, you have a gas phase. Sometimes it's a question of the viscosity in the materials. You have a film like shown here, but sometimes you have droplets on the graphite particles, and that changes the chemical reaction. So here on the right-hand side, you see the plant, which you can find my institute in the lab. Here you see the the reactor, here the flue gas pipe, the post-combustion, here we combust the phosphorus to P2O5, and then we scrub it and produce phosphoric acid. So that works quite nicely. I was thinking, what about the primary rock phosphate? It would be interesting to use that. And my team and me, we spent some time in Morocco at a conference and visited companies. And then it turned out, well, it's not so easy to change the process for the primary process of phosphorus production because they're used to it and it just runs. But when you have a closer look at the phosphorus production, you see there are many steps necessary for that. And you see there are a lot of waste materials. You see it on the right-hand side. You have gypsum, you have tailing ponds, you have rock piles, and that's a big problem for Morocco because they just don't have the space to dump it somewhere. Part of it goes to the sea, diluting the sea. So the next thing is it would be nice to use exactly these residues because the people in Morocco get rid of it. For us, for Europe, it would be quite valuable. And so we had a closer look at that. But we started with the rock phosphate just to get an idea how it works. To have what contents of phosphorus do we talk about? Well, in the rock phosphate, we have about 33%, which is quite a lot, of course. But if we talk about the waste rock, it's close to 17%, tailings 14%. So good switch sludge ash has maybe 20%, as mentioned earlier, but sometimes we have just 10% or even less. So they have waste material with 17%, about 17% phosphorus, and that's really, really a lot for us. So same procedure as earlier, we have the rock phosphate, we need correction materials as explained earlier, then the carbothermal reduction takes place. We need a reducing agent as well. We were talking about this graphite bed. So we could use that as this carbon as a reducing agent, but that would mean that we spend parts of our packed bed, which is not desired because we would like to keep the particles there. But therefore we add a carbon resource like charcoal from biomass. And for energy, a couple of years ago, energy from producing heat with electricity was not very desired for an engineer because you have coal, produce steam, produce electricity, and then you produce heat again. But now it's different because if you talk about areas with huge potential on solar energy and wind energy, sometimes you don't know how to transfer it, how to store it. And this would be exactly the perfect region for using electricity for this kind of chemical reactions. So the same as explained earlier, we have here the desired red area. We see the materials we are talking about are far away from this area, but if we combine them properly, we come into this red area. So this desired area, we can treat it. Here another word, which I didn't mention earlier, what is really important is, of course, the melting behavior, especially in this type of reactor. We see we have rock phosphate, pure rock phosphate in this example, mixture without iron and mixture with iron. And you see the behavior is completely different. And here we have in the first case the first picture at the top, then quite high temperatures, and it didn't change a lot. At much lower temperatures, in the mixture 1, it melts at comparable low temperatures compared to the first case, and similar in the mixture with iron, but it looks different. So this melting behavior, the viscosity is different. And this may affect the chemical reactions taking place in the reactor. So, what is the conclusion of our first experiments? We could transfer 99% of the phosphorus into the gas phase. And that's much, much better than the traditional Wöhler process, which is quite nice. And we could avoid phosphogypsum, which is important as well. So the next step is to work with these residues on the right-hand side, number 1 and number 2, to see how it was not so easy to get these residues from Morocco. The rock phosphate we got from a company in Austria, but it's not so easy to transfer this kind of materials from Morocco, not because of the mail, but you need the permission to do that. And that's not so, was not that easy. But we will handle that, because now we have cooperation partners in Morocco. So, next step, this is the last example I will talk about the recycling of lithium-ion batteries. Why is it important? If you have a look at the right diagram, at the moment you have a global lithium cell demand in gigawatt hours of about 700 within the next, it was 2022. This will increase 25, about 1,700, and by 2030, which is just 6 years away, we will have about 4,700 gigawatt hours demand. This is quite a lot, and at the end of the life, we have to deal with this waste material. So the available battery material for recycling, at the moment, of course, it's not that much, but within the next 10, 15 years, it will increase dramatically. So it's on the one hand side, we need the processes to deal with it, and these processes have to be kind of economically as well, because otherwise it will be hard to incorporate them. So if we talk about lithium-ion batteries, they are containing various different materials, and we have to treat them all. You see here what the kind of species we have. So we have carbon, nickel, lithium, aluminum, cobalt, copper, and so on. So quite a lot. And we have many different batteries, and all these batteries will end up in the waste one day, and we need processes which are able to treat this variety of the different batteries. So there are different routes. We have the pyrometallurgy. The advantage is you can recover nickel, cobalt. The disadvantage is the lithium goes into the slag and not into the gas phase, so it's not possible to recover it. Hydrometallurgy, we have high recycling rates, so colleagues in Leoben, non-ferrous metallurgy work in this field. There's a high use of chemicals and process stages, many stages, to come to this performance. But they are quite flexible to different input flows. And there's also biometallurgy possible. You use ecological leaching materials, bacterial cultures susceptible to copper contamination, but the throughput is quite low. But you see there are many different steps when we talk about lithium-ion recycling. We have the collection, the pre-treatment, then you get the black mass, and then you have the barrel metal recovery, refinement. So it's quite complex. What are the challenges or disadvantages? If we talk about the transportation and collection, it's a safety problem because the batteries may tend to self-heating, especially when they are damaged. The pre-treatment is not that easy because we have standardization problems. We have different designs, different materials, so we would need different pre-treatment. The material recovery, we have variable chemical compositions of the batteries. And the material process in the recovery processes, we need purity levels to bring them back into to the industrial processes. So my part is high temperature process technology. So we are talking about pyrometallurgy. We need the pre-treatment, as mentioned earlier. We smelt it, and then we refine it. But this classical pyrometallurgy has the problem that the lithium ends up in the slag. So, what we come back to our innovative reactor concept, this inductively heated bed reactor. Now, the electricity for heating it is an advantage. It used to be a disadvantage until 10 years ago. Therefore, we can talk about a kind of zero emission approach. Although I don't like this word too much, zero emission. And we can reuse the mineral fraction, the alloy, and we get the lithium and phosphorus as well, which you find in the black mass. So, similar approach as I mentioned earlier. We're running experiments on that. Here you see this, for example, is a picture out of our experiments. You see the lithium, which was formed very clean in the gas phase. The oil, as it is, can go back to the industry, but still we are, what I should mention, we have a European patent since a couple of months, and Canada and the United States is pending for this process. So hopefully we get it in a couple of months, this patent. Yeah, but as I mentioned, we have a whole process chain when we talk about recovery of lithium-ion batteries, and we are dealing mainly with this thermal processing part. So we need the off-gas treatment, we need treatment of the output material, the mechanical pre-treatment, and we are working on that. And having partners already in some areas, but we're still open for partners in these other processes which are necessary for effective recycling process. So we are to end this year. We are talking about phosphorus, which is quite dangerous, white phosphorus. We are talking about high temperatures, so we have to talk about safety as well. We have a very strong safety group at the institute. We have a safety lab. We do explosion experiments, self-heating experiments. We do a lot of simulation work, and we also started a new master course, Safety and Disaster Management. So we are in the second year now, and duration is 4 semesters. It's taught completely in English. And what is new for Leoben, it's open to all disciplines. So on the bachelor level. And that's the first time in Leoben. So they are not only engineers, but they come from each discipline. And what is new as well, we don't talk about technology and economy. We include the nature and human aspects. When you talk about safety, the human aspects are really important. When you talk about crisis communication, when you talk about resilience, you have to understand the human being. And therefore, this is a very important field in this course. We try to design this master course in a way that it's always also possible as part-time study, because there are many students working already in industry and they would like to take these courses as well and do this master degree. So this was the technical part. A few last slides to say thank you. First of all, to you. I just have a picture of you and your colleague, not of everybody, but thank you for this nice welcome, for your hospitality. It's really great to be here. I learned a lot, plans of the Crete dishes, and of course also professional things. I would like to thank Susanne Feil, because she helped me to organize this day. This was very important. And of course to our rector Peter Moser for supporting me. He was really happy to hear that I want to join you and stay here for a while. Of course, thanks to my group, not only for their great work, but they prepared many slides. And when you download the slides, you will see they will go really into detail, which would be far too much for this presentation. I would also like to thank my wife, because while I'm living in Kanyal, she stays in the south, in Kasumisi, hopefully still watching me and waiting for me, because I spent a weekend in Kasumisi. Yes, and I apologize to my part of my institute, because they have a soccer team and they don't name it. They didn't name it of my institute, but they translated my name Raupenstrauch to Caterpillar Strauch, and they won the last championships. And the championships for this year are ongoing right now. So 2 days ago, they had their first 3 games out of 5, and they won all the 3 games. Next week there will be the final. So I'm sorry I cannot support you at the moment there. Yes, and then I thank you all, online or here, for your attention, and keep on running.
Well, Harald, thank you very much for the presentation. Very, very excellent work that you do there. Not that everyone of us relates directly to the specific work, but it is excellent work that you do at the Open, and we're very happy that you're here and we have the opportunity to discuss joint cooperation, either for educational matters, joint programs, or research projects. I would like now to ask the people, either in the room or maybe online, to if they have any specific questions.
Yes. Okay. I would also to congratulate Professor for the excellent presentation. A lot of the subjects you have presented are very interesting for our department, the Department of Mineral Resource Engineering. And I'm going to communicate these slides to other colleagues who are not present at the moment because they have other problems. Some of these subjects has been also in the past, or even now, are under, let's say, study in our department. We had, I personally have engaged in a project that has to do with thermal activation of the modest concrete in order to produce, let's say, a new concrete by thermal treatment.
I see.
Yeah. I don't know if you have, let's say, in change in these topics which have to do with the process of construction demolition of waste by thermal techniques.
It's interesting. We didn't have this in mind. We have colleagues at the Crete University of Technology who work with and on concrete. So we are working on the secondary raw materials and how to treat them, but we were not thinking of treating the concrete itself.
Yeah.
Which is quite interesting. So it's worth to talk about that.
Okay.
Yeah?
Okay.
Thank you.
So I guess I can have the presentation, of course, to share it with my colleagues.
We have Harald Raupenstrauch give us a much longer presentation, which is stored on our cloud, and then we can share it with all the.
Okay, so I will make an announcement to my colleagues in my department, because I'm sure that a lot of the subjects we have explained to us are very useful also for a lot of them.
And there you find more details, also chemical analysis and many more. And then the discussion can go much far into that. But of course, there are so many different topics, and you need some time to read everything. And this is just, I would say, this presentation is kind of a teaser.
Yeah.
So give you the feeling I want to know more.
Yeah.
So at this point, let me say that Professor Diagilakis has raised his hand and
somewhere at the airport, right?
Yes. Hi. Thank you very much for the very interesting and very entertaining presentation. I hope you can hear me well.
Yeah, perfect.
Sure. Okay. I can't wait to see the full slides, actually, to dive into the differential equations that we were talking about briefly last night, right? I have one brief question for you. I see that the very high temperatures that you operate with is a common aspect of most of the processes that you described today. So I come from a process control and optimization background. So I was interested to know how difficult it is to control those kinds of processes because of the very special circumstances, such as high temperature, and whether in some cases controlling them or making sure that you're doing the procedure that you follow is right requires to destroy the final product to make further, analysis of what you have produced.
Yeah, you're completely right. It's not easy to control it. Well, we can handle it, not too bad, but it would be nice to measure the temperatures in this reactor in more detail. And since it's you have these magnetic fields, it's not so easy to measure the temperatures inside. So this is something we're really interested in to improve this measurement technique. We maybe need something completely new, but we're the wrong person for developing it. And because if the temperature has a big influence on the viscosity on the one hand side, and therefore on the chemical reactions, and also on the chemical reactions with the crucibles, because otherwise you have ocean, and then you destroy parts of the reactor. So it would be really nice to get a better insight during the operation into what is going on in the reactor. You're completely right.
Thank you very much again for your answer and for the presentation. And I wish you a pleasant stay in Crete if you're planning to stay longer.
Yes, I'm still stay here. But next week, my wife will join me in Kenya. So it's enough for her in the south. She will join me back up and get a second bed for her.
Thanks again. Thank you very much.
Thank you. It was a pleasure meeting you.
It was a pleasure meeting you too, Professor.
Thank you.
How about scaling up? Because if I understood correctly, your reactors are either large scale or pilot scale.
Yeah.
I mean, would that be more difficult to control the temperature inside the reactor when you scale up, or?
Well, actually, the measurement of the temperature, yes, but we put a lot of work in it in the scale up, and we have the design, the basis for the scale up. We have it already, so we did it. But the scale up is difficult because of the large money you need for that. So you need companies who are interested in funding it, and therefore it was important to get these patents. And now we have the patents. It took us, I think, 3 years to get it, and now it should be easier to get companies who are interested in the scale up. And from this point of view, we have a good design basis already, and then we have more detailed information on the energy consumption, because the energy consumption, or demand I showed you earlier, is for a small reactor. But of course, the heat losses and everything for a small reactor are much larger compared to a big reactor. So I don't like to talk about the heat losses too much, because in a large-scale reactor they are much lower. But we have the basis for that, and we just need funding partners, actually. And of course, we have to put some more work in the gas cleaning system. Here we are open for partners as well, because we are more in the thermal reacting part of all my colleagues. One of the colleagues is Harald Raupenstrauch. They developed a concept for the gas treatment in our lab, but for a large-scale gas cleaning unit, we would need some more input and partners.
I have also one question. First, thank you very much for your very nice presentation, very informative. Regarding the wool waste, you mentioned that it simulates somehow basalt rock or something.
Yes.
Right? Yeah. So very recently I was starting some application how this kind of waste of basalt contributes to mitigate CO2 emissions. For example, the basalt, when the basalt withers, the rock somehow they are affected by withering, then they can release cations and different kinds of elements. And this kind of elements, then they can react with CO2 to mitigate CO2. So there are some studies that calcium and silica and probably iron and some other elements, they can react with CO2, like what we mentioned about CO2 emissions. So they can control CO2 and they can convert this into a new mineral, and they can mitigate somehow the emissions from that. So maybe the direction is more environmental.
But important point. You're right, but I guess you need a large reaction surface, you need the wool, and you need the time. So in this case, it would be necessary to make wool out of the wool residues. At the moment, we were talking about granulating them, but there are thoughts of producing wool again. But you need there used to be one company in Styria as a partner to see how this secondary basalt can be used for wool production as well. So this is one thought, which would be a direct circular economy, because it's only circular if you a direct circular when you use the product out of the recycling process for the same product. It's the same is true for the battery recycling. So we have both in mind, but mainly we are working now in collaboration. But in this case, the question is when this reaction with carbon dioxide should take place. Should it take place before you use it as insulation, or when it's mounted already on the houses and then they react with carbon dioxide? or you're treated with high concentrated carbon dioxide.
Yeah,
but
the
it's-
idea is how to store and that's how you can reuse the carbon dioxide.
It would be interesting to see what amount it could be, what is the impact on it, but it's an interesting question. Thank you.
I have a question, maybe you can elaborate a little bit about this the new master's program that
Yeah.
on safety disaster management, that you combine all the technical aspects with societal aspects and so on. Could you just give us, elaborate a little bit about this? Because that would be very interesting. We have a couple of courses here in our university, but we do not have a separate program.
Yeah.
That would be very, very interesting to see, whether we can combine something that will also be of interest to us.
Mhm. Well, first of all, my idea was I'm an engineer. So, and as an engineer, I had to learn that the human aspects are important. And so, from my studies and my work, I was dealing with safety in the industry. In my private time, I'm a winter mountaineering guide. So I was dealing with risk assessment in the mountains. And there I learned they have different approaches, and not only because they have a different background, even the cultural aspects are completely different. So if you talk to a winter mountaineer guy, winter mountaineer from Tyrol and from Styria, they have a different approach. And if you talk about industrial safety in Austria, in Italy, in China, well, it's completely different. So even my lectures would have to be different according to the country where I give the lecture. So that was the main idea. So the technical part, plant safety, plant and process safety is more or less the same. But what we also have is lectures not given by engineers, so we have a lot of lecturers from outside in this case, therefore this master course is more expensive than all the other courses because we have, I would say, maybe 1/3 of the lectures are given from outside, from geosphere, for example, on nature and weather conditions. We have social aspects from psychologists, psychotherapists on crisis communication, on resilience, and I did not prepare, unfortunately, the list of the lectures, but I think it would be quite interesting maybe to combine it. What I did when we started with the new course, I was also talking with Susanne and others. Maybe there are lectures which could be offered from EURECA-PRO partners. We had one lecture on critical infrastructure in the past from a partner. So we're dealing with that questions as well. So and maybe you have lectures which could fit into our program and the other way around, because it would be nice to do it hybrid or online, and I come back to Crete all the time whenever you want. So Crete is one of our most favorite areas, my wife and my favorite areas, so I would be happy to come back for lecturing. So, but I can prepare this material in more detail and we can have a chat on that next week.
Yeah.
Okay.
Jessica, say something? Yeah. We're now working on this subject that Professor Yamamoto mentioned about the joint degrees. We are looking at this time and the top priority is the joint degrees in Master of Science programs.
Yeah.
That's why we have special interest on this type of course here.
That was the reason why I decided to talk a little bit about this program, because to be honest, we have more than 250 applicants for this course right now from all over the world, which is far too much.
Yeah.
Because not all the applicants have the background to take this course or these courses. So my idea is to look for more strategical partners. For example, we have a visiting professor now from Serbia. They have very well-educated students. They are working in they have similar master programs, and that was the idea, to maybe get a strategic cooperation in this field as well with your university. Because I know your programs, the quality of your programs, of your work, and how you deal with this kind of problems. So I think this could be very, very fruitful.
Okay.
So if there are no questions from the remote audience, I would like to actually thank Professor Raupenstrauch for this nice talk, and under the circumstances, I hope we did well, because we had to change the venue at the last minute.
It was perfect. So I really like it. So it's kind of an exile. We are here because the university is blocked. I saw it this morning, and the student explained me in detail why. So it was, for me, it was quite interesting. So we're in exile.
One thing from your talk that really strikes me is, if I understood correctly, in the industry there are many thermal processes or processes where you have to heat some kind of material at some really high temperature, and then all the energy that could be used while the material cools down goes wasted in most cases. Is this my understanding?
Yeah,
you proposed some ways to take advantage of that, but it seems that in general this energy is not exploited.
There are huge amounts.
Say a few things
there are huge amounts, because this dry granulation, for example, we had I skipped this part of the presentation. We had a pilot plant with a diameter of this granulate of about 2 meters, and we fed it with 700 kilograms of slag at temperatures of 1700 degrees centigrade. And it worked quite nicely, and the first turbine built one in Linz at the blast furnace with a diameter, I think it was 8 or 10 meters. But it's not so easy to handle it, because the slag, the properties of the slag vary at different temperatures, the behavior changes, and if the viscosity changes due to temperature property changes, then it can happen that you produce wool on a granulate. So it's not that easy. There is maybe one more step necessary. But there are other possibilities. You can produce a hot granulate and then cool it in a packed bag, just an open packed bag. This is possible. We are investigating that as well. So there are possibilities, but I think maybe the pain is not enough so far, because we are really losing a huge amount of energy.
Are there any more questions?
Maybe my wife asks Harold, when do you come home?
I don't see any raised hands, so I guess everybody's happy.
Okay, so we can wrap it up here. Harald, thank you so much.
Thank you very much.
It was a pleasure to have you here, and we really enjoyed your talk.
Thank you.
You gave us a lot of food for thought. for future cooperation, and of course, you're gonna be with us next week.
Yes, I will be.
So we will arrange individual meetings with professors, and you can discuss all these ideas.
And then I will check whether you had a closer look to my 125 PDF. No, I'm just kidding.
Κάποιος ήταν στο chat, ποιος ήταν το ίδιο.
It was a thank you note
Okay.
by Aphrodite.
Okay, thank you very much.
Thank you very much.